So when Richard and I put the programme together for this meeting, we thought it would be very good if we had a talk from someone here at UCL, a younger member of staff, but carrying on the tradition of the type of calculations that Patrick was so pioneering in. So it's very good that we've got David Scanlon and can tell us about computational chemistry research at UCL.
Thank you, Rod, and I'm delighted to be here to talk today. I have to say, I have no experiences of Patrick, unfortunately, but to tell you a little bit about me, my name is David Scanlon. Obviously, you can tell by the accent I'm Irish, but I just accepted a position here in the Department of Chemistry as a lecturer, and also based in the Diamond Light Source. And as interestingly enough, today, as my first duty as an academic, I had to do 6 FIVAs. So as I was watching the students come in, their faces full of fear, I come down here to give a talk, and I have my undergraduate research project 5 examiners here, my transfer report 5 examiners here, and my PhD 5 examiners. So I can see exactly where they're coming from. Today I want to tell you a little bit about the current research that's going on here in the chemistry department at UCL, specifically based in the Kathleen Lonsdale building. So it's a rather waffly title, A New Thermodynamic Tools and a New Explanation. You'll see exactly what I mean as I go forward. So what I'm especially interested in, and what is a big research goal for a lot of the community, is computational materials design. So targeted materials design, being able to actually predict materials, predict their properties accurately, and being able to actually provide guidance to experimentalists. So we're moving towards a time where we can accurately do this. The accuracy of the computational methods that we have is ever increasing. As you can see, there are some blimps when you think of something like ice, but we're getting there. So there are 2 main approaches that people tend to use. One is crystal structured database mining. So you can go through the crystal structured databases, try swapping anions and cations in and making new materials. And this has been quite successful. It's especially done in the batteries field. Gerd Cedar has championed this, and the TCO Cedar is moving into this. Water splitting as well. Cedar seems to be moving forward. Solar cells is the NREL, National Renewable Energy Labs, have a big project on this. Magnetic materials are based in Dublin, Professor Sanvito, and zeolites. But you can also do crystal structure prediction, where you don't actually give it any information to start with. You start off with the cation and anion combinations that you want, and you can use genetic algorithms or some kind of sophisticated search method, or you can actually just put the atoms in a box and be slightly inelegant, but still quite efficient. So the computational methods are definitely becoming more accurate and more robust, and also the computational power is increasing, so there's more we can do. So to really move this forward, you need your robust methods to simulate the geometry of the electronic structure, and we're moving that way. There's new methods coming online, new packages. You can screen things first with atomic potentials, then you can move to ab initio to get more accurate electronic structure information. But one of the things that you face is that when you predict a material, how do you actually know that that material can be formed? So the first checkpoint is, what is the stability of the material? Can you look at its thermal stability? Now, if you're doing something like an ab initio method, you're likely to be doing this at 0 Kelvin, but that still gives you plenty of information about whether this material can be formed or not. So as you move to try and predict new materials, it's not just binary materials. You're looking at ternaries, you're looking at quaternaries, you're looking at putting in more chemical degrees of freedom, the more elements that you put in, but unfortunately that ramps up the complexity of what you have to check to see if the material is stable. So here in the chemistry department, we came up with a program called CAPLAP. So it trips off the tongue easily. Chemical Potential Limits Analysis Program, and so we shortened it to CAPLAP, which is fun to say in the lab. So most of the programming for this was done by my colleague John Bookeridge, who's also Irish. Just get that in there. So essentially what you do is you assume that the material can form, and then you build constraints around that so that it won't dissociate into its elements, it won't be less stable than competing phases, and that would be binary, ternary, quaternary, to however many elements you actually want. And so you solve them, you have a nice procedure, and I won't spend too much time going through it. I'm going to show you exactly what you can do with CLAP. So the first system that we were looking at was barium stannate. So this is just your simple, well not simple, but your less complex ternary system. So last year this material became very, very interesting, and I'm going to tell you why. It's a simple cubic perovskite, but note that barium and tin are more earth abundant than a lot of other elements, so this makes it interesting straight from the get-go. It has an indirect band gap of between 3.12 to 3.26 experimentally, and a direct band gap of 3.4 to 3.5, so it's optically transparent, so light passes through this. But in 2012, 3 papers came out reporting that this material, when doped with lanthanum, possessed mobilities of 320 centimeters squared per volt second. Now, this is significantly larger than any of the transparent conducting oxides which are used in industry. It's better than indium oxide, and indium oxide is the industry standard and the one that everyone wants to move away from because indium is so expensive and there's such a volatility in the price. So this kind of leads to some questions. Why are these studies suddenly finding this high performance in these samples? Because previously this has been tested. So in the 80s and 90s, a lot of people did work on lanthanum and antimony doping of barium stannate, but they didn't get good results. So essentially, the simple reason seems to be that they've now developed a way to make single crystals. If you make a powder or you make I'm going to say poorly deposited film, you get lots of grain boundaries and the conductivity falls away. But when they make a nice single crystal, they found out that the material actually has properties which are far greater than indium oxide. So what we wanted to do was we wanted to look at barium stannate and see, is it actually an ideal conducting oxide? So we can turn to our ab initio calculations. This is done with the VAST code with the PBE0 hybrid functional. And so we calculate an indirect band gap of 3.22 eV between the 4 point and the gamma point, and the direct band gap is 3.68 at the gamma. You find that the oxygen 2p states dominate the valence band, as you'd expect for this type of oxide, and the conduction band states are tin 5s. But which is the most interesting is that the effective mass of the conduction band minimum, which is nice and dispersed, is actually only 0.22, which is lower than it is for indium oxide. So this is kind of explain why you would get reasonable mobilities. But also, if you just examine the conduction band makeup, you can see that there's a very large separation between the conduction band minimum and the next highest conduction band. And this is necessary because in a truly degenerate N-type TCO, you want the electrons to populate the conduction band, but you also don't want the electrons which are here to be able to be excited to the next unoccupied state. So you really need that large separation. So from an electronic structure point of view, this material has all of the properties that you would want. So just to show that it's not just a calculation giving me a funny result, we also did some work with some experimental colleagues in Binghamton in the US. So they actually contacted Professor Sang, showed him this guy who can make these fantastic single crystals, and asked him for some samples. So they took them off to the ALS and they did XPS and hard XPS, and you get, here they are plotted here with our comparison to our calculations. You see excellent agreement, but one thing you should notice is that the hard XPS shows conduction band fitting. So these are lanthanum doped samples. So the electrons are definitely going into the conduction band. This is exactly what you want from a new N-type TCO. You want the electrons in the conduction band, you want degenerate conductivity. And we also did XAS and XES measurements and compare those to some calculated PDOSs, and we see very good agreement again. So essentially, we now have the proof, experimentally and computationally, that this material does have the electronic structure that you want. So going forward, to look at the thermodynamic stability of this material using CLAP, you set the formation is limited by the calculated enthalpy of barium stannate. Then you have to set the limits that it won't form into its different elements. You also don't want to form other binary limiting phases, and also you don't want to form a ternary limiting phase. So you calculate all of these properties with your method of choice, and you plug it into the CLAP, and that outputs a very nice diagram showing you the stability field in chemical potential space. So this is just a 2D plot. You can get a 3D plot. You can basically play around with this as much as you want. One thing that you should note is that if you don't take into account Ba2SNO4, you will of course get a larger stability field. So you have to be very careful in your choice. You have to do every single one of the limits that are there. It's a pain when you get to quaternary materials, but it has to be done. So when you want to actually calculate defects in this material, the consistent way everyone does it is formation energy of a defect is equal to the energy of the defect in the charge state Q minus the energy of the host plus n times the elemental energy plus the chemical potential. And this chemical potential is the numbers that you effectively get from Kaplan. So not only have you looked at the stability, you're able to put the numbers into the defect chemistry, and you can compare the chemical potentials as to the environmental growth conditions. Now obviously we can't factor in temperature yet, but that's something we want to move to in the future, but it gives you an idea of what happens under oxygen poor conditions, under tin poor conditions, under barium rich conditions, whatever it is what condition you want to grow in. So we did a range of defects in the system. So intrinsic N types, just oxygen vacancy, tin on a barium antisite, tin interstitial, barium interstitial. So P-type defects. We tried different hydrogen positions because in these materials hydrogen invariably acts as a donor. And we also tried extrinsic donors, so lanthanum, antimony, and fluorine. So we can take, so here we have this red square corresponds to this point here, which is oxygen poor, and the green one is going to correspond to here. So differing growth environments to show how you can change the defect chemistry. So you can quickly see that under the oxygen poor conditions, the oxygen vacancy dominates. This is the formation energy of the defect on the left. This is the Fermi level between the valence band and the conduction band on the x-axis, and the solid dots indicate thermal ionization from one charge state to another. So we can see that the oxygen vacancy dominates under oxygen poor conditions, as you'd expect, but the ionization level from 0 to the +2 charge state is actually quite a bit below the conduction band, so it's not a shallow donor. So we can quickly see by scanning under the oxygen poor conditions that you will not get a degenerate semiconductor from this material unless you donor them. You have to put donors in. And under P-type conditions, the formation energy of the charge states of the P-type defects will actually charge compensate all the donors. So if you grow it under oxygen-rich conditions, metal poor, you will effectively get an insulator. And as you move to extrinsic defects, we can see that pretty much lanthanum on the barium site is an excellent shallow donor. You don't get an ionization level in the band gap, which means that the electrons are donating directly to the conduction band. Fluorine on an oxygen site is actually a very good dopant as well. Antimony on a tin site doesn't give you the same behavior. You end up getting an ionization potential which is just below the conduction band. You can just about see it there in green. So that would explain why lanthanum doping seems to be the most successful and antimony doping doesn't seem to work. So now at the moment in UCL chemistry we're actually testing fluorine and hydrogen doping because no one has tried that yet. So I have the Marcus group, we're going to synthesize some films that we're going to get to measure the diamond hopefully. So conclusions from this part. Barium standard is actually a very promising earth abundant alternative to ITO. You get the perfect conduction band electronic structure, and you definitely do need to have extrinsic donor doping. You won't make this, it's not intrinsically conducting, you have to put donors in there, and we get confirmation from our experimental collaborators that it is actually a degenerate semiconductor. We get the direct evidence of conduction band filling. So now we move forward to a quaternary system, because we want to test Kaplan and show that it works. So we picked lanthanum copper oxyselenide. So this is an interesting material because unlike most materials, it's a degenerate P-type semiconductor, which is very hard to get. There's a band gap of 2.8 eV. As you can see, you get a nice bit of dispersion at the valence band, which should give you good hole mobility. It's been successfully used in a number of applications, but there are still some unanswered questions. You get these high conductivities experimentally, 910 Siemens per centimetre, but it doesn't experience a Moss-Bernstein shift. So one of the questions is why? And why is magnesium the optimal dopant? And magnesium is nowhere near the same size as lanthanum. You would expect calcium or strontium would fit in much better. And if this material is truly degenerate, one of the dreams is, could you actually dope it to make it transparent via a Moss-Bernstein shift? Now, I honestly don't think this is possible, but we'll go on that anyway. So again, we do this time HSE06 in hybrid functional and advanced code. It's a very nice tetragonal structure where you have layers of copper selenite and layers of lanthanum oxide. We get a direct line gap of 2.71 eV at the gamma point. Experimentally, it's about 2.8, so we're doing quite well. And as I said, really nice curvature at the valence by maximum. So this is what we want to see. But when you want to actually see if this material is stable, you have to do all of the different limiting phases. Now, when you're playing around with hybrid functionals, you have to do, there's 23 limiting phases here, as well as the elements. And some of these contain copper 2+, which means you have to check the magnetic ordering. So it's quite an endeavor, but if you're willing to do it, you can do it. Just hope you have a lot of extra time. So moving forward, you can actually put this straight into Complat, and it outputs you a nice 3D picture where we've held selenium constant here, and you can get an idea of the size of the stability field in chemical potential space. Which then you can get, there's 20 different thermodynamic limits that we had, 20 different intersections in that strange shape in the box. And you can plot the formation energy of all of the defects in a horrible picture, because I can't figure out a better way to do it yet. And you can quickly see that at different growth environments you can get vastly different behaviors. So a lot of them which we consider as copper poor, the copper vacancy dominates in the neutral charge state. But under certain conditions, you can actually get selenium vacancy dominating. So if you just look at the intrinsic defects, you can see that under typical copper poor conditions, which would be actually the intersection with LACU SE2 and LA4 SE304, which is one of the beauties of that, tells you where these limits are. And you can see that the copper vacancy is by far the lowest energy defect, and it is not compensated. It's quite shallow, it's about 0.15 of an EV above the valence band. So for P-type oxide semiconductors, this is actually very, very impressive. But it is by no means a degenerate defect. So essentially, you will have to activate it to make this conduct. It's not going to be a degenerate semiconductor. But if you're not careful, and if you did happen to grow it under selenium poor conditions, you find that the copper vacancy is actually compensated by the selenium vacancy, and you get an insulating material which won't show any kind of conductivity or good properties at all. So care needs to be shown, and also it shows the importance of doing this properly with that, because if you don't have these limiting factors in, who knows what phase of chemical potential space you'll actually be in. So turning to acceptor doping, magnesium on the lanthanum site, this is the blue one here, is higher in energy than the copper vacancy. It's also higher in energy than calcium on the lanthanum site. More importantly, it's way higher in energy than strontium on the lanthanum site. So why experimentally is this the best dopant? It doesn't make sense. So we started to think maybe it's a compensation mechanism. Maybe something is compensating strontium and calcium and magnesium is winning. But we tested many different compensation mechanisms. So the dopant taking up a copper position, the dopant forming next to an oxygen vacancy, the dopant forming next to a selenium vacancy, which isn't shown here, and basically nothing fits the bill. As far as we can tell, strontium should be the ideal dopant. Why is it magnesium? I have no idea. And experimentally, they don't know either. And they didn't like it when I said this to them. So, conclusions from this. Copper and selenium mixing at the valence band maximum yields a very highly dispersed valence band, which is what you want. So ideal for P-type conductivity. The growth environments are vital, and this is where Complat comes into its own, especially as you move to these multi-ternary systems. The copper vacancy is a dominant defect, but is not shallow, and strontium on the lanthanum site is the lowest energy acceptor. I'm pretty happy that at any level of theory will tell me that. So further experiments are definitely necessary. Conclusions. It's a nice efficient method to calculate these thermodynamic stabilities. We have now, it's just been accepted, it's in press at the moment in computer physics communications. It outputs the stability field to GNU plot, Mathematica, and as a TXT for Grace. And you can also do a grid of points showing the change in formation energy of a defect across the growth environment, which is quite useful. And this type of analysis is vital for trying to look at defect chemistry physics of material and for trying to draw comparisons and guide experiment. And my explanation is today talk a little bit about rutile and anatase. So TiO2 is the most widely used oxide for photocatalysis. And last year alone, there was over 10,000 papers on web of knowledge on TiO2. So TiO2 is a big business. It has two main polymorphs. Everyone knows anatase and rutile. Rutile has a slightly smaller band gap, but anatase is a better photocatalyst, and rutile is a poorer photocatalyst. But when you bring these phases together, you get this mixed phase anatase-rutile samples. They show much improved performance. And to be honest, all of the explanations in the literature don't really hold up. There's many different theories flying around and nobody really knows. And so one of the questions is, what actually is the origin? In 1996, Cavan et al. Placed the conduction band of anatase 0.2 eV above that of rutile using impedance measurements. This is currently the accepted model, so what we wanted to know is this actually correct? Why should the conduction band of anatase sit above that of rutile? So there's three alignment models that are kind of bandied around in the literature. You have this one, which is called the normal model by Cavan, where you should have electron flow from anatase into rutile, and this is actually quite a small offset, so there's discrepancies as to whether this is actually perfectly equal or whether anatase is slightly above. In 2007, Scott Chambers' group in PNNL measured the work function of anatase and rutile, and they found that the work function of anatase was 0.2 of an EV bigger than that of rutile. So this kind of reverses that alignment. So now you're starting to wonder what is going on. And there's loads of detailed EPR experiments showing that the flow of electrons goes from rutile into anatase, and holes go from anatase into rutile, and they base this entire model on this normal model and claim that it's defect levels which are making the electrons flow rather than the actual band alignment. Now, I can accept defect levels for rutile, but for anatase, when you donor dope anatase, it's a degenerate semiconductor. You can niobium dope anatase and it's basically like a metal. So you're not going to be looking at defect levels. Maybe on the surface, but definitely not in the bulk. So a simple analysis of the bonding in TiO2 shows that, as you'd expect, oxygen 2p states dominate the valence band, and the conduction band edge is dominated by TiD states. And if you kind of examine the upper valence band, you see that the widths are about the same. So neither would experience a chemical broadening, which would affect a band offset, meaning that the band edge position should probably be determined just by the on-site electrostatic potential and the optical dielectric response. So we took a step back and we said, maybe we don't need to use ab initio to describe this. Maybe we can actually just look at it using an interatomic potential. So we calculated the Madelin potentials using the polarizable shell model, so fitted to reproduce the high frequency dielectric constants, and we quickly found that the valence band maximum of rutile should sit about 0.47 eV above that of anatase, just based on the Madelin offset. And this would also place the conduction band about 0.17 EV below rutile. So this is favouring Scott Chambers' initial 2007 alignment. So we also decided that we'd go a little bit further, get a little bit more complicated, and we'd also calculate the energy of the charge carriers propagating at the band edges using the Mott-Littleton approach. So this is not a new technology. This is something that could have been done years ago. But again, this agrees with our Madelin alignment. So the valence maximum of rutile should be 0.39 above anatase, and the conduction minimum of anatase should be 0.24, so around the same offsets. And we went one step further and said, well, it's unlikely that the current people are going to agree with an alignment stemming just from an intercommon potential. You're going to get everyone who's into electronic structure calculation saying you can't really do that. So we decided to do a QM-MM alignment. We did our embedded cluster. This is Alexei and Richard's speciality. So you have your QM region, your interface region, and an MM active region, and then you have your MM frozen region. This allows you to have access to the vacuum. So when you calculate the ionization potential, it actually means something in light and vast. So quickly, we found out that the ionization potential we calculated for rutile was 7.83, and the ionization potential we calculated for anatase was 8.3. So an offset of 0.47 eV. So this was consistent. We did this on a range of cluster sizes, and we didn't get any change in the offset. So this is the offset we're getting from first principles. We're kind of happy with this because we calculated ionization potential of zinc oxide is 7.71, which is 0.12 eV higher than rutile, which we calculated here. And the experimental offset that's seen is 0.14. So we're getting numbers that make sense. But all of our calculations strongly suggest that the accepted alignment model is wrong. So independently to seeing our results, we asked the experimentalists here in UCL Chemistry to grow some samples and measure the XPS alignment. So Charlie Dunnell grew the samples, and Rob Palgrave and Ivan Parkin did the measurements. And we grew it in a 1-to-1 ratio, 1:2 ratio, and 2:1 ratio, so we'd be able to understand which way the core peaks were going. And we found that there was a valence band offset of 0.39 eV. So completely independent of our calculations, they came up with an alignment which matches what we expected. And again, goes against the normal model. So this gives, at the interface, an effective band gap of around 2.8 eV. So we believe that this is the origin of the increased performance of the mixed phase, because you have this shortened band gap at the interface, and you have electrons flowing from rutile to anatase and holes going from anatase to rutile, so you're getting a hole and electron separation. So to conclude this, we've done an analysis of the bonding analysis of rutile, and we think that the valence band and conduction band should be determined by Madelin potentials. Our alignment model shows that the valence band of rutile should be 0.47 eV above that of anatase, and the Mottler-Littleton approach supports this. Our QMMM alignment supports this, and now the XPS supports this. So we believe there is a type 2 alignment with a reduced band gap of 2.8 eV, and we think this can explain all of the unexplainables over the last couple of years. So to conclude, I would like to thank John for doing all the coding flap, Alexei Sokol, Scott, Andy Logsdale, Steve Shevlin, Matt Farrow, and also Richard for making the KLB a great place to work for the last couple of years. Aaron Walsh in Bath, Graham Watson in Trinity, Charlie Donald, Rob Palgrave, and Ivan Parkin here in the chemistry department. Materials Chemistry Consortium for access to Hector to do computing, the Infrastructure South for access to Iridis, and for the last 2 years I've been funded by the Ramsey Memorial Trust and the MAPS faculty, so for funding my fellowship. Thank you for your attention.
Thank you very much, David, for bringing us up to date with interesting developments. It's an interesting talk, so have some questions. Yeah.
So you showed, you look at the band alignments together to using absolute ionization for the 2 phases. Do you think that in a real system made with different types of materials, the actual interface itself will have some effect on the band alignment?
The interface will have a huge effect, so you'll get all kinds of band bending, but we were looking at the perfect bulk alignment. So once we have that understanding, we can go somewhere and work out something else. But
I think it's very, very interesting, and also it's, I discussed it with Alexi before. There was one strange effect which was observed many years ago, that the TiO2, it exists actually in amorphous form.
Yeah.
And its band gap is larger
Yes.
than rutile.
Yeah.
Not anatase, but
Yes.
rutile. And this goes against the disorder, any disorder models, right? So
Yes.
because it's supposed to be lower band gap. So I think this is something to do with the nature of that is very, very similar to what you're showing here. But I think your explanation about the maximum potential is very, very simple and very, very interesting. Now, here's the question.
Okay.
There is, so the maximum potential, right, is more or less linear with the volume. Right? Oh, well, okay, with the lattice constant, let's say.
Yeah.
Now, there is a slight density difference between the anatase and rutile. So if you just align the densities and look what happens to your maximum potential, will it explain everything? No? It's, I mean, it could be even simpler than maximum potential itself, right? Because if it's a density question, then
I think it is the maximum potential, but it's the, okay.
yeah.
Okay, you could use the density as a very simple way of.
Yes. So if I bring the density of rutile to the density of anatase, will I get the maximum potential very close or closer?
Okay, so that's
Probably very
Yeah.
similar, yeah.
Yes. So possibly there is kind of information.
yeah, true. So are you thinking there's an interface effect as you bring the two materials together and you get a kind of
You just the density, that's the difference effect, and then you know mismatch. It's small mismatch effect of this.
Particle size effects. Rutile and anatase exchange their thermodynamic stability in the nano-sized particles.
yeah.
So, is the size possibly involved in playing difference in playing any role in the results?
No, because although we call it a cluster, it's an infinite model. So this is bulk. Yes.
What if you did make a cluster?
I've seen some people have some cluster models out there and they have results varying all over the place, but we've never done it ourselves. I have no feeling for how much an effect that will be, but it would be interesting to look at. Yeah. It's a different type of calculation.
Yeah, when you do a plot
Yeah.
for these quaternions, is it possible to get an absolutely definitive list of all the other compounds you must check it against? I'm just thinking how easy it is to perhaps miss a possible competitive phase.
This is the problem. You have to hope that in maybe a structured database that there are all of the limiting phases. And
Right.
if some don't exist, you're in trouble. And you're probably talking about trying to do crystal structure prediction yourself to find the limits for the material you're trying to do crystal structure prediction on. That is a problem, but I mean, you could do it if you had